After preparing our 0.02 molarity stock solution, we made 3 dilutions. These solutions will have concentrations between 10 to the negative fifth and 10 to the negative second. For our first solution, we add 2.5 milliliters of stock solution to a 25 milliliter volumetric flask and carefully add water to the mark. For the second solution, we take 2.5 milliliters from the first diluted solution and add that to a 25 milliliter volumetric flask and carefully add water to the mark.
For the final and third solution, we take 2.5 milliliters from the second solution, transfer it to the 25 milliliter volumetric flask, and add water to the mark. If ever the solution became cloudy, we added 10 drops of ammonia.
Note that our set of solutions decreases in concentration from left to right. The molarity for these solutions was calculated using the molarity 1, volume 1 equals molarity 2, volume 2 formula. Here is our table and calculations. We transfer our diluted solutions to cuvettes in preparation for the spectrophotometer. The spectrophotometer allows us to measure absorbance in a solution. We start by zeroing the spectrophotometer to remove interference caused by the water molecules. To do this, we take a blank containing water, wipe two opposite sides of the cuvette with the chem wipe, then place the blank in the spectrophotometer and hit 0 on the computer.
Once we've completed this step, we can start scanning our solutions. The stock solution is scanned first across all wavelengths because we need to view the various wavelengths so that we can determine the best one to use for finding the absorbance of the copper amine solution. The point where absorbance has the highest peak is the lambda max, and that's where absorbance needs to be measured. We perform spectrophotometer readings for all the remaining dilutions, making sure to wipe the cuvette on two opposite sides each time. The absorbance values visible on the computer screen are recorded in our notebook. For the third dilution, we continuously got negative readings even after zeroing the machine and double checking that we had wiped the cuvette. We believe this is because our third dilution had a lower absorbance value than the blank. Since we did not have time to make a new dilution, we made do with the data that we could use.
Now we get the absorbance value of our unknown solution. We make sure we've zeroed the spectrophotometer and wiped the cuvette. Here's our absorbance values and our concentration versus absorbance graph. The relationship between reduction of light through a solution and the solution's properties can be explained with the Beer-Lambert's law. The components of this equation include absorbance, molar absorption coefficient, molar concentration, and optical path length. Molar absorption coefficient is equal to the slope of the line from our concentration versus absorbance graph. Note that concentration and absorbance have a linear relationship. Failing to zero the machine would lead to an inaccurate graph that misrepresents the relationship because it would be including the absorbance value of the solvent. Molar concentration comes from the molarity we calculated for our solutions. Optical path length is the cuvette's length, which is normally 1 centimeter. All these components can be used to calculate absorbance. To determine the concentration of the unknown solution, we use our graph and our understanding of Beer-Lambert's law to create an equation that will help us find the concentration. Before leaving the lab, the equipment and station must be cleaned.